Okay, here's our example for the position vector and velocity vector to orbital elements problem. So this will be a good one to use when you do your project to check your code. So basically you can just plug in the position and velocity vector that we're going to be given and then see if you get the same answers that we get for orbital elements. Alright, so we're going to be given r, which is position vector, and that's going to be negative 6045I minus 3490J plus 2500K, and that's in kilometers. And then we're also going to be given a velocity vector, so negative 3.457I plus 6.618J plus 2.533K. And that's kilometers per second. Alright, so we have those two vectors. We want to find the 6 orbital elements. So we want to find A, E, I, the little omega, capital Omega, and then true anomaly nu. Okay? So all we need to do is basically follow those steps that we had in that last video to calculate these things. So first thing is going to be to calculate E. So remember you have that eccentricity vector formula. So let's write that out. So that's v squared over mu minus 1 over r times the position vector minus 1 over mu times r dotted with v times v. So you just need to take the magnitude of the two vectors that you were given, because you need the magnitude of r here, and you need magnitude of v right here. Okay, I don't know why I was pointing over here. Anyways, okay, so find the magnitude. So we'll have the square root of negative 605 squared plus negative 3490, square that, and then plus 2500 squared. And that's going to be 7414.32 kilometers. And then do the same thing for V. So we're going to have a square root of negative 3.457 squared plus 6.618 squared plus 2.533 squared. And that'll be 7.88 kilometers per second. Okay, so now we have those two magnitudes, so now we're ready to plug everything in up here. So your eccentricity vector will be 7.88 squared over mu, so we're going to say that that's at constant value, 3.986 times 10 to the 5th, minus 1 over 7414.32. That was just that value we just found. Now you're going to multiply that by this position vector. So here's your position vector here. So I'm not going to read it all out, but just write it back down. So there's your position vector, and then we need to subtract 1 over mu. So there's that. And multiply that by r dotted with v, so you would need to do the dot product of these two vectors. So remember the dot product, you would just have this times this plus this times this plus this times this. Right? So once you do the dot product, you get 4133.25. And then write out the velocity vector. Like that. Okay. So now we have that, so go ahead and do those calculations. And then once you do that, you get the three components. You get IJK components. So you're going to get negative 0.090992I minus 0.0142117J plus 0.026157K. So now you have this vector, you can do the magnitude of the vector to get E. And remember magnitude, you can do it just like you did it there. So for this you get 0.171. So that's your eccentricity for this orbit. So 2, you're going to calculate A. So basically you're just going to do those equations we listed before. So remember H is R crossed with V. So you're going to get HI times I plus HJ times unit vector J plus HK unit vector K. Alright, so I'm going to assume everybody knows how to do the cross product. So do the cross product. Once you do that, you end up getting negative 25385.2 I plus 6669.49 J minus 52,070.7 K. Alright, so remember, this is HI, this is HJ, this is HK. And then the magnitude of this is 58,311.7. Okay. So now that we have this magnitude, we're going to use that parameter equation. So remember that's h squared over mu. So plug these values in. Mu is still at 3.986. So we have that. And then once you do those calculations, you get 8,530.48. Okay. And we know the parameter P is also equal to A times 1 minus E squared. So we'll say 8530.48 is equal to A times 1 minus 0.171 squared. So A is our unknown, that's what we want to find. So solve that for A and you get 87.43 kilometers. Just like that. Okay. So pretty simple so far, right? Not too bad. Okay, step 3, this will be to calculate I. Okay. So remember, this is your inclination. This gives you that angle, tells you how much tilt you have in your orbit. So we're going to have the dot product between H and K. Remember, that's equal to HK, and that's got to equal the magnitude of H times magnitude of K cosine I. And this magnitude of K has to go to 1. Okay. So we already found H in the problem above, so you don't really have to do that again. You already know what the values are. So we need the magnitude of H, which was the 58,311 number. So we already got that. And we need HK. So HK was right here. So we'll just use that. So I is going to be the arc cosine of negative 52,070.7 over 58,311.7. So I will be 153.249. Right? So that tells you how much tilt you have. Okay. All right, so we got 3 more of these to do. And we'll talk about these more in class next week, just to make sure everybody understands it. I just wanted to make sure you guys had plenty of time to figure out this material for the project. All right, so step 4, we're going to calculate capital omega. Okay, so just to repeat the equations we had, this deals with that node vector. And remember, the node vector pointed towards the ascending node. So that's equal to k crossed with h. And we said we'd get two components. So we have ni times unit vector I plus nj unit vector j. So now if we take k and we cross it with the h vector that we had right here, so if we do that, let's write this down so we know what the vectors we're using here. So we'll have k cross negative 25,385.2 I plus the 6669.49j minus 52,070.7k. All right, so do that cross product, and then your n vector will be negative 6669.49i minus 25,385.2j. So now you've got your vector. You can take this, do the magnitude, get n. So that'll give you 26,246.7. Okay. All right, so now that we have this, now we are ready to find capital omega. So remember that is equal to the arc cosine of the I component of n over the magnitude of n. So we have all of that information now. So we'll have the arc cosine of negative 6669.49 over 26,246.7. And that equals 104.721 degrees. Now this is one of those, remember where I said you'd have to do an if statement in your MATLAB code, because you need to check for the angle, right? So this is the one you need to check to see if the j component of n is less than 0. So the j component of n is right here, so obviously that's a negative number. So that's less than 0. So that means capital omega, I keep putting equal, is greater than 180 degrees. So that means we need to get this angle changed over. So we're going to say capital omega is equal to 360 minus the 104.721. And then this will give us our final value. So 255.28 degrees. All right, so that's your capital omega. And that was this angle right here, just as a reminder, okay? Okay, two more of these. So 5 is going to be to calculate argument of periapsis, so that's that little omega. So this one was the angle between that node vector and the eccentricity vector, so we have the dot product. N and E. Looks like that. So all you need to do basically is plug in your values here. Okay. So N dotted with E, once you do that dot product, you get 4214.54. And then when you multiply the magnitudes of those, you get 4488.19. So now that we have this, you can just solve this. We'll have omega equals arc cosine 4214.54 over 4488.19. And that equals 20.11. So again, this one you need to check and see what the sign is. So we're going to do E dotted with K, which is greater than 0, because the K component of E was 0.026157, so that's a positive number. So that means this omega value is good, so we can have 20.11. And finally, last thing, we're going to calculate true anomaly. So we have E dotted with R, and that equals ER cosine nu. So we're going to have negative 0.090992 I minus 0.142117 J plus 0.026157 K, and then dot that with R. I don't know why I'm writing all this out. You guys already know what these are. So R was negative 6045 I, and then minus 3490 J plus 2500 K. All right. So do that dot product. Once you do that, remember you always get a scalar with the dot product, so you're going to get 1100, 11.43. And then we're almost done. So there's your dot product. We need this product of the magnitudes. So once you take the magnitude of this and this, multiply it together, you're going to get 0.171, that one you already found, times 7414.32. That gives you 1,267.85. So now you can find nu. So it's the arc cosine of the 1111.43 over 1267.85. So that gives you 28.76. And as we saw in class the other day, you know, you can have two true anomalies at a given R. So gotta check for the signs. So for this one, we do R dotted with V. That's greater than 0. So that means the true anomaly should be less than 180, which this one is. So that means this one is good. We don't need to change that one. So we're going to have 28.76. Okay. So those are the steps you need to do to complete one of these problems where you're given position and velocity. You need to get to orbital elements. This is essentially what you do. And you're going to do these same things on your project 1. Okay? All right, guys. Hopefully I'll see y'all on Tuesday. Have a good weekend.